Engineering 305. This is a lecture on section 5 from chapter 8 on singularity functions. Let's get going. What are our learning objectives? Well, our learning objectives 21. We're on learning objective 21. We are going to derive the singularity function required to describe the beam equations in a single equation. That's cool to me. That's just cool. The way we're going to do that is we're going to use this whole new branch of mathematics that we haven't done before, and we're going to introduce it in 10 minutes, and you're going to be experts at it. But they're called singularity functions, and what might be hard to see is that this is not a parenthesis, but it's this caret. It's a less than, greater than kind of bracket that's being used to create that function x minus xo raised to the n. And that's our equation. That's our new feature. And what this is it's a value. It's something that has value on the right side of the number line, but not on the left. And so that's what we're going to learn about today. So this singularity function is something that it creates a term which has value conditionally. And so we can put that into the equation, and much of the time, or I'll say half the time, we're going to ignore the term, and half the time we're going to use the term. And that which half we use it on is set up in the equation. It's set up. It's an equation then that's only true on the right. It's only true on the positive side of the number line. It's not true on the negative side of the number line. And so this system works really well if our beam equations start from the left as we derive them. And that's one of the reasons why I know what's coming, right, in the class. So I taught so that I was always starting on the left and working over towards the right. So you remember that beauty that we did at the beginning of chapter 7? We had this beam 8 feet long, and it had a distributed load and a point load and 2 reaction forces. And we got equations that were conditionally true in a sense that I have a shear equation that I had to write down in 3 different chunks, because one chunk is true for 0 to 2 feet, and one chunk is true for 2 to 6 feet, and then the other chunk is good for the last 2 feet. Well, I could do the same with the moment equation that was also taking place. But now, using this new math, we'll be able to do this all in one equation. And that, when we're trying to do this integration, will make our jobs easier. So if we started out, and I do this section, if I make a break here, and I do this section just on the first section, right, we would have, I've got to add a VR, and I can add my MR. It just depends on which equation I'm going to solve for. But now some of the forces in the y direction, and I'll put on my coordinate system, traditional Tübingen kind of approach here. Some of the forces equal to 0 are equal to, well, I have my reaction force at A, and that's going to be true anywhere I go, that reaction force is going to show up. And I have minus VR, and there aren't any other terms. So that first section led us to VR is equal to the reaction force at A, which in our case, and you can see it right here, our reaction force was equal to 1,400 pounds. Now what we need to do is go and write our equation for the next section. And let's do that on the next slide. If I break my beam there, now I got to put my coordinate system back on, right? Y, X, and I've got to put my reaction forces, VR, MR, The only one I'm going to use is the v because I'm just going to do the sum of the forces in the y direction equal to 0 or equal to. Now, we would still have this reaction force, which I should have drawn in, that reaction force at A. Then I'm going to start with a term that didn't show up before, and that is minus x minus 2 times w. Now, we know that term. We've done that in the past. But this is this additional term, and then I'm going to subtract VR. And if I reorganize that, I'm going to get VR is equal to RA minus x minus 2 times W, and I'm going to leave it like that for now, just for right now. Now I'll rewrite it. 1400 minus, well, that's going to be, W was 4, or 400, minus 400x plus 800, right? 800, not 8,000, 800 equals 2200 minus 400x, which is what we're seeing up above there. But now I want to say, look, all we did, it's always simple with me. It's all we did. We added that term because that term is conditionally true from that point over. And that's where a singularity function comes in. We can write that down now as a term that starts at x minus 2. It starts at x equal to 2 and continues to the right, but doesn't show up on the left. And we could rewrite this expression. What would that look like? Well, first let's introduce the singularity function a little bit more. So here we introduce our singularity functions. Yeah, it's the same slide. I just cut and pasted it. And it's got this funny little shape, but that's all that we know that this is different than just a parentheses. It's got the caret instead of the nicely rounded shaped parentheses. If we use that caret function and that becomes a singularity function, then x minus xo raised to the nth power, this term right here, becomes x minus xo to the nth. We just replace the carets with parentheses. If n is greater than 0, that is, n has a positive value. We don't want negative things there. We just want the positives. And we are at a spot where x is greater than xo. We are to the right of x0 on the number line. If that's not true, if the exponent isn't positive and we're not on the right of the number line, then that value is just equal to 0. And we ignore it. All right? And then I've got a special case where if that exponent is equal to 0, and that's this one here, then x minus xo is just equal to 1. It's just used to add a value, 1. And so that way I know that like if I needed to add a constant, I can put x minus xo to the 0th power, and then anything to the right of xo will be equal to the constant. So, and we'll see this play out. Then where this comes in and where this gets interesting is I want to give you, and these aren't necessarily rules, we could derive these if we wanted to go through the calculus, but the rules for integration and the rules for derivatives. And I think the rules for derivatives are easier to follow. I think derivatives are easier to follow. So if I take the derivative of x minus xo raised to the nth power, you know what it's going to be. I'm going to take the n times x minus xo raised to the n minus 1, and that's what's listed there. And if you can see that, then you can do the antiderivative or the integral. the integral of x minus xo raised to the n is going to be 1 over n plus 1, that's pretty standard, times x minus xo raised to the n plus 1, except I've got to add a constant. I've got to add that constant. Well, this is what we've been doing. This is what we've been working with for all of chapter 7, half of chapter 8. And now we can start to apply this to the problem that we just had. So let's go back. I'm going to start with this problem, which I'm going to write down. If I do sum of the forces, I'm not going to put the coordinates, if I do sum of the forces in the y direction equal to, and I'm putting an arbitrary break at some point, and it's got a reaction force VR, but I'm not telling you where. If I do sum of the forces in the y, well, I know I have a reaction force at A. I'm going to leave this as symbolic, sorry. And then I'm going to, and nothing else. At the end of this equation, right, I'm going to put a minus VR, because I'm going to work from left to right down my beam and say, okay, where is this stuff true? Well, I've got a reaction force at A, and then I go along, and all of a sudden at x equal to 2, so now I've got this, my function turns on at x equal 2, and I start to add this shear load. Well, if I were going to write it down in a traditional way, it would have been minus w times x minus 2. And then this equation would be true if I took my break in that zone, right? Well, we've got this new tool. I can rewrite this equation. I can rewrite this. Here's the new method. I'm going to do it in blue. R minus W times caret x minus 2. Now, according to the rules, the value of that is x minus 2 as long as I'm over here on this side. All I have to do is change that shape a little bit, and I'm all good. Now I'm going to keep going. I still have my VR on the other side over here. I keep going. I keep trucking along my beam. Tip, 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 toe. And then I come to this. That load. I've got a point load. Minus. It doesn't have. I'm just going to call it a P. It's got a constant P. I've got a force P acting down. And I should put that in this equation. Sorry. Minus P. But now I need this in this blue equation, my new blue equation. I need to say that it's conditional. So I need to put in a singularity function. And where does it turn on? Well, it has to turn on at 6 feet, and then it's always going to be there, but not before 6 feet. X minus 6. But now I'm not multiplying. This isn't, see here I was multiplying by x minus 2, which is what I need to do. This one just needs to turn on and off. So I have to change this to the 0th power. Now that function turns on and off. And I could keep going. I could add plus a reaction force at, well, this is A, B, C. Oh, it's even right there. Plus a reaction force at D times x minus 8 quantity to the 0th. That's a singularity function. And now in one equation, I can look at anywhere on that beam. I'm going to rewrite that. VR is equal to RA minus W times the singularity function x minus 2. minus p times x minus 6 to the 0th. Let's talk about this term a sec. Does that ever come into play? No, it doesn't actually, because while that force shows up here, there's no beam over there, so there's no equation beyond x equals 8. The beam equation doesn't work beyond x equals 8. So I don't even have to write that equation down. I just write this down, and that's what I get for my beam equation for the entire beam in one shot. I know this term only comes in play for things to the right of x equal 2. This only comes into play for things, and you can think about how we derived our equation and any section, and that whole thing works. Now we've got a couple tricks we're going to have to do, but there's a couple tricks that also are really cool that I need to show you. Let's keep going. Let's rewrite that equation. Oh, I don't want green. This is my new equation. This is new blue, which is an engineering trick I use, by the way. When I'm doing revisions in CAD and when I'm showing pictures of my stuff, I'll often put the new version of what I'm working on in blue and the old version of what I'm working on in gold, so that you can compare the geometry right next to each other and see the differences and know which version of the part you're looking at just based on the color. New blue, old gold. And it has nothing to do with University of Michigan. VR is equal to the reaction force at A minus W times the singularity function x minus 2 minus P times the singularity function x minus 6 raised to the 0th power. Okay, that gave me the momentum equation. Or sorry, the momentum. That gave me the shear equation. I want to integrate that. Well, that's no big deal. My moment equation is equal to RAX minus, how do I integrate this? Well, it's W over 2 x minus 2 singularity function squared minus P singularity function x minus 6 singularity function, and then now that's going to be to the 1st power. I suppose maybe I should put that, maybe not. I'll leave it off. I forgot my constant. Now let's take a look at that a sec. RAX, this is my first term, right? Does that make sense? Well, yeah, if I would split that there, then I would got the reaction force here, RA, and the value of that moment that it makes is RAX. So that's good. And these start making sense. But now this is, let's look at this for this last equation right here. Oh, I don't want that one. I kind of, see, I've already got the constants all plugged in. That's okay. Let's plug in the constants. We'll simplify it. We'll show that we equal this, and then we'll go on. So this is RAX. So this is 1400 times x minus 400 divided by 2 is 200. And then you've got to multiply, right? Because that's just a regular function. I'm going to just multiply that out. As long as I'm going to work this for the 6 to 8 foot portion of the beam. So then if it's true, then this, if we're on that last portion, if we're beyond 2, then this term just becomes x minus 2 squared. So that becomes x squared minus 4x minus, plus 4. And then I've got to add a minus 2000 x plus 12,000. I multiplied that one out. I could do that. Minus minus became a plus. Am I going to have trouble with sign errors here? It's a minus minus. Nah, I'll be okay. So first, let's look at the x squared terms, right? That's how we simplify that. Equals That's the only x squared term I have. Minus 200 x squared. Hey, look at that. Boom. Right there. Let's go to the next term, which is going to be the terms that involve x. So I've got, I'm going to go plus x times 1400. I've got a minus 200 times a minus 4, so it's going to be a minus 800. So it's plus 800. And then a minus 2000 times x. And so that's going to give me, well, 14 and 18 gives me 2600. No, 2200. Minus 2000 is going to give me a 200x. Oh, look at that. Did I get my sign wrong? I got to erase to figure out if I got my sign. No, I got my sign right. Plus 200. I have a plus 200 here. We can keep going, but you can see this equation that I wrote down, boom, 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 it's pretty straightforward. Now, here's what I want us to look at. Here's the next thing I want us to look at. Every time I hit a change in my beam, right, which is how I call out A's and B's and C's and D's, that's how I label my beam. Every time I hit a change, I wrote down another term in my equation. And each of these terms behaves individually. I don't need to look at all of them at once. Each one of them becomes its own little standalone island. I integrated that, and then I can do math to simplify it to get to that version of my equations. But I don't need to simplify it at all. I can just leave these as terms because when I integrate, they all stand alone. And when I integrate, the rules for each term fit that term, and then I just add my other terms in. That really can make this a lot easier too. Let's keep going. If I look at this system, reaction at A, W, P, reaction at B, I could make it more complex. I could add a moment somewhere. If I look at VR equal to, I get this term shows up right away because it's at x minus 0 raised to the 0th power, right? I know you're still struggling with the singularity functions and what they mean. But here's what I want you to look at. This is because this term looks a lot like this third term I had down here. This term down here I had was minus p times x minus 6. Singularity function, sorry, raised to the 0. Why do those look the same? Why do those look the same? Well, let me tell you what's going on here. First, that's the force that's applied. This value here, this 0 or this 6, that's the position in which we apply it. That is, whatever value I put in for that constant. So now it's going to be a force, not times that, times the singularity function, sharp corner, x minus, we called it XO in our table. XO is the location where I add it. And now when I do x minus XO, the function isn't true for the left, but it is true for the right. So the reason these terms look the same is because they're both just forces that have been added to my beam with the position called out. Interesting. Now, those show up in the shear equation, And that's why they get a 0th power. I almost have to start one equation back. So in chapter 8, we introduced this idea of this load equation. And the load equation was really just the derivative of the shear equation with respect to x. But we didn't really do anything with it. Well, now we're going to start to do something with it. In this scenario here, I can write down my load, and I'm not even going to glorify it with its own symbol. I'm just going to call it load. My load equation would be equal to, follow the process, W, whatever my load is, x minus 2 raised to the 0th power. And so if you think about that beam, that function, my load equation, if I plotted it, it starts out as long as I'm to the left of 2, it has no value. So that line just goes trucking along at 0. And then at 2, it jumps up to 400. And supposed to go straight over, but okay, that was really bad. It just goes straight over at 400. That's my load equation. This all ends, none of this has value past 8, but that's my load equation. Whew. Now I've got to do a couple more things. So I've got to integrate that to get to my shear equation. So my shear equation, sorry, I want to go with blue, new blue, new blue, new blue. Oh, let's go with navy though. My shear equation is equal to, well, I integrate my load equation. So it's going to be equal to the integral of, well, that's going to be minus W. Sorry, it's not minus W. Yeah, it is. My WX down. I don't know if I got the sign wrong on the previous slide. I apologize if I did. Times x minus 2. There's my singularity function. I integrated that plus a constant. Now, here's where things get funky. I'm actually going to add a couple constants. It's a constant for this part of the beam. It's another constant for that part of the beam. But here's my constant. And you're just going to see this is actually a constant. V is equal to, I've got the reaction force at A, and that's times x minus 0. And that's a singularity function. That is true anywhere beyond 0. It's not true behind 0, but the beam equation doesn't work below that. But it's a constant because that's to the 0th power. This now is to the 1st power, right? I integrated that. And then I've got my next term, which I'm going to put in as the minus W x minus 2. And I'm going to put specifically that it's to the 1st power so that we recognize that. And then I've got minus P times x minus 6 raised to the 0th power. Now, if you look at this through a particular set of lenses, that's a constant. This is equal, this term here, that term is equal to 0 or 1. And so this term is a constant. And here's another constant that plays in a different part of the beam, but those are just constants. Huh. That's kind of funky. Now, here's the other part that I want you to see. So that goes into there, is I dealt with this as a term all on its own, and it became that. Let's keep going. I want to write my moment equation. Oh, who's not using the right navy? My moment equation is equal to, well, you got to kind of remember what we had. It's RA times the singularity function. I had x minus 0 raised to the 0th power. Well, I integrate that one, and I get x minus 0 to the first power, and then I would actually have an exponent here, right? But we don't need to put the 1 there. That would just be silly. Minus W. Now, this was x minus 2, because that was my position, raised to the first power, so I need to integrate that. So it's x minus 2 squared, and then I have to put the exponent underneath. So it's W over 2, x minus 2. And then I have to put a minus P x minus 6, and I'm going to put to the first power. And I'm going to add a constant, because I have to add a constant when I integrate those. Does that make sense? Yeah, we can integrate. We can do that. And if you look, if you remember 4 slides ago, that's what we had. Now we had it as parentheses. We had RA times X minus W over 2 X minus 2 squared minus P times X minus 6. And we showed that that equaled that right there. We showed that. So this is good. Now, here's the interesting thing. These terms I can all look at independently, and I can keep going. So I'm going to integrate that to get my slope, and then I'm going to integrate that to get my deflection. Let's jump ahead and do that. My deflection looks like delta as a function of x is equal to RA. Now, I know you got to remember, and you got to maybe flip back and forth in the slides, RA times my moment equation had x minus 0 raised to the first power. So I'm going to integrate that to get slope. That's the second power over 2. And then I integrate that again, and I get the third power over 6. Okay. Minus, if you think about what the W equation looked like, it was a term W. It already was 1 power greater. And so this is going to be x minus 2 to the 4th over 24. Why? Because I integrated it one more time. This is the 3rd over 6. This is the 4th over 24. Remember, this term and this term look the same. X minus 6 cubed, x minus 6 cubed over 6. Oh. I'm trying just to erase it, and I'm running into trouble. That term and that term are load terms. Those come from the shear equation. They got integrated 3 times, so I get a cubed over 6. And that's always the way they're going to look. And I get these are shear terms. This is the load term, W. That is my load per foot. Those I have to integrate 4 times. I get, what I should have put on here was C1x plus C2, because those are the constants that I get when I integrate. But my equations are always going to look like that. And these are the way that my terms are going to show up every time. A force, that's a force. This is a distributed load. What I didn't include is a moment, because this problem doesn't add a moment. If I added a moment, that would have shown up as a constant in my moment equation. I would have integrated that twice. And so moment terms are going to look like a moment times x minus xo squared over 2. But now we can just look at a system and write down the equations. RA has a positive sign because it's acting in the positive direction. Minus W because it's acting in the negative direction. Minus P, it's acting in the negative direction. And now we can go in and solve for boundary conditions, and we've got our equations. I think this is pretty cool because what you guys have been working up to in little stages, you're now at a point where you can look at a beam and write down the equation, and then we get to solve the boundary conditions. We made it that much easier, but I think that's pretty slick. I think that's pretty slick. So we'll do an example problem. In fact, maybe we'll do this problem here, and then we'll be on our way and we'll learn a whole new technique for solving this. I guess one last comment I should make. One last comment I should make is that as we look at this, when I say that, I said this at least twice, this term is independent of this term and that term. They're independent. And the reason that's important is because in the next section, chapter 6, we're going to talk about using superposition to put loads on top of other loading situations. And using superposition, one of the things we had to have was that these are linear and independent. And that's what we've got here. So my deflection is a function of the load, and it's linear with respect to that load. Yes, this term, it's not linear with respect to position, but it is linear with respect to the load. So that's an important thing that's going to show up in section 6. So I hope you're doing well. Don't worry, more to come. We'll run an example problem, and but I hope somewhere in this lecture this process clicked for you, and you could see I can just write these terms down, and I need a little bit of practice, and that's what homework's for, and we'll get there. So, all right, don't worry, more to come.